So, welcome to Math 1033. That's the technical name for it. This is Calculus 2. So, a couple things that are important for everybody to sort of understand. So, as those of you who had me before know, I am not, I always found it interesting the first day of class, like an instructor comes in and like reads you a syllabus. It's kind of ridiculous. I mean, you guys are all educated. You can read, I assume. So the syllabus will be posted to Canvas tonight. Part of your first assignment will be to read the syllabus. You will be asked questions about the syllabus, like what's the textbook, how many points can you earn, stuff like that. Obviously, if you have questions about the syllabus, you can email me. But anyhow, I don't want to waste too much time on that today. What I'd like you to do is go to Canvas and check that out as soon as you get a chance tonight. It's not published yet. It should be ready sometime this evening. So, you could check it out tonight or tomorrow morning, whatever's easier for you. But what I do want to do is briefly go over a couple important things. First off, number one, so the course is run just like Calc 1, after we went online. All right, Ricky. Ricky, you got to go upstairs. No. Hold on. We got a code red. Ricky, you got to go upstairs, sweetie. Got to go upstairs. Come on. Come on, Ricky. Come on. Upstairs. 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 Find the bike later. You got to go upstairs. Go upstairs. Upstairs. Go up there. All right. Old habits die hard. Here we go. Welcome to Learning with O'Grady and his crazy kids. All right, sorry about that, but such is life during the Roni. So essentially, here's what's going to happen. We will meet. By the way, ignore how sloppy the handwriting is. I have to have more practice. It's been a few weeks, and I'm trying to write on this tablet thing, but I have multiple screens, and so I have to look in different places. So it's hard to be really neat. So hopefully, you'll be able to follow along, and if not, you can ask questions. So what does it mean that it's run just like last semester? So here we go. We'll have what I like to call Zoom lectures every Tuesday and Thursday at 1. Now, technically, we're supposed to be meeting from 1 to 3, or 1 to 4. There's no way that that's going to happen all the time. It might happen once or twice where we're sitting here for 3 full hours, but that's very much very unlikely. We all have human attention spans, and that's just too long. So you can imagine that on average, these sort of lectures will last anywhere from like an hour to 2 tops. Instead, what I'd like to do is give you other supplemental stuff to watch at your own time and place. I just don't know that sitting here for 3 hours straight is the best way to learn this. So we're going to have to, don't forget in the summer, it's not a regular length semester, so everything's, condensed a little more. And we'll make sense of that as we go. But the thing to keep in mind is you're not going to be trapped sitting at your computer for 6 hours a week listening to me talk. It'll be a lot more lenient and spread out than that. One of the things that I know is on most of your minds. So these lectures are not. How do I say this? I mean, you're not. Let me put it this way. Maybe this is a better way of thinking about it. I don't take attendance. Hopefully, you can attend them all. We'll put attend in quotations because that amounts to you watching a video at a computer. What I do and what I did in the past, and I don't know if it was useful or not, but I will upload. So all the lecture material to Canvas. So you'll have these whiteboards that I'm writing on now. You'll be able to find those on Canvas. I will also embed the lectures into Canvas. They'll be on YouTube, but you'll be able to watch them on Canvas or wherever you want to watch them. So essentially what I'm saying is I hope you can make these live lectures because that's the best way to learn this. But if you can't, you're still going to be able to go back and watch them. Does anybody have any questions about that right now? Okay. The next thing that's important to understand, this next topic is textbook is not required. But let me be very clear. I am highly recommending it. I'm not going to force you to spend a couple $100 on something, but I am highly encouraging you to do it if you can. Whether you buy the physical book, which looks like this, or you buy access to what we call the digital content, or if you go on the internet and find a PDF of it somehow free or illegal, I don't know. I don't care how you get it. If you have another textbook, maybe a slightly different, an older version, or maybe a friend of yours took calculus and has a calculus book, that book will most likely work, so you should reach out to me. What I'm saying is if you don't want to spend the money or don't have the money to spend, that's okay, because I'm not requiring a textbook. I will never ask you to do something specific from the textbook. However, this is the book we're going to follow, and that's why it's on the syllabus. So if you have questions about that, you should email me, and we'll go from there. Does anybody have any questions? Okay, great. So the other thing that is worth pointing out is your grade. How will your grade be computed? Well, it's going to be 10 homeworks for 100 points and 3 exams for 300 points. So that is 100 total. Or excuse me, 400 total. So essentially your grade is evenly going to be determined by 3 exams and homework. They're all worth the same weight. So the details of all that, they are on the syllabus. So please read it, and if you have questions, let me know. Comments, questions? Okay. Okay, so then if you guys don't have any course-related stuff, and we all understand, well, if you have questions, please ask, but there's not much else to say other than let's get right into the math, because, again, this is a continuation of Calc 1. Oh, yeah, so Michelle asked in the chat, is there extra credit? Yeah, there'll be extra credit again. The details of that are on the syllabus, so I would encourage you read that. And if you have questions, let me know. But it's the same as last semester, Michelle. It's the My Math Lab. So some of you are familiar with My Math Lab. When you buy a copy of the text brand new, or you buy the digital access, it comes with a code, and that code allows you to access all sorts of online software. Now, I don't make that mandatory. Some instructors do. Instead, I use it as extra credit for those of you who want to buy the access. So if you want to buy the access, you can get extra credit. So someone asked how many weeks summer session is. Well, it runs from today until August 1st. So when you look at the syllabus, you'll see, or if you look at a calendar, we start today, so that's 1 week, and then next first week of June is week 2, and then 3, 4, 5, 6, 7, 8, 9, 10 weeks is essentially what the summer is. Now, mind you, a regular semester is 16 weeks. So we're learning all the same material in 10 weeks instead of 16. So it's going to be fun. Any other questions? Did I miss any? No. Okay, so if at any time you have a question, you know the routine, just ask. So what is Calc 2? That's a question we might want to know about. Well, the short answer is it is a continuation. Continuation of Calc 1. And so at the end of Calc 1, we were, how many times am I going to write we? I'm French. What we were doing is we were studying the definite integral. And the indefinite integral. So what did that look like? Well, it looked something like this. It was these symbols. So it's worth reviewing what this concoction of symbols means. And how we can go about computing them. So let's review a few things. So the definition of this integral if you recall, the way it was motivated using, I don't want to say using, that's a bad way of saying it. So it wasn't motivated using something, it was motivated by what we called the area problem. And you might recall what the area problem is. What was the area problem? It was the following. So basically it said, given a region in the plane bounded by the graph or graphs of a function or functions, what is the area? So this was a question, and we're going to draw a picture here to sort of, in case you don't quite remember what we mean by this. So let's give a different color. So let's imagine I have my XY axis in the plane, and I have 2 points. I'll put one here, we'll call it A. I'll put the other one over here, we'll call it B. And then I have some function, and it has a graph. So maybe this guy looks like this. And what we're interested in is between the points. So let's remind ourselves this could be some curve. So it has a algebraic description, which we generically denote as y equals f of x. And then what we are wondering is, what is the area of some particular region? And the region that we would be sort of interested in would be this. So if I sort of shade this region in, what we found is the following. We have to be very careful with how we write this. So the number that has this name was defined in such a way so that it gives what we call the net area. Of the green region. So you might recall that a lot of time was spent doing this, at least when I teach it. We spend time doing these Riemann sums and discussing these ideas of limits. And in particular, we had this very scary definition. And we had that the integral from A to B was equal to the following limit. The limit as n goes to infinity of a sum, k goes from 1 to n, remember this scary stuff, of f evaluated excuse me, at these points, which we called x sub k star times delta x. And these symbols all had meaning. Delta x was given as b minus a over n. And what was x sub k? X sub k was a plus k times delta x. And that was for k equals 0, 1, 2, all the way up to n. So this is a very, very complicated definition. There's lots of symbols. For most people, the first time they see it, the first few dozen times they see this, it's very overwhelming and it's scary. But that is the definition of the integral. At least our definition in Calculus 1. Does anybody have a question about this? Now, good news. And by the way, if I go too fast, just yell. If you need me to move back, I'll be happy to go back. I don't know until you tell me what kind of speed I'm at here. So, that definition is difficult to use and just looks, for a lack of a better word, scary, as my kid would say. It just looks scary. So we luck out, though. There's very good news. Luckily, we had this big, powerful theorem. So we have the fundamental theorem of calculus. And if you remember, if you look back in your Calculus 1 notes, the fundamental theorem of calculus had two parts. And the second part was this sort of super duper shortcut, so to speak, for computing an integral. So what does the fundamental theorem of calculus say? It says that this integral, instead of using that scary limit, can actually be evaluated quite simply. It can be evaluated by taking g of b minus g of a, where g prime of x equals f of x. So that is what we call an antiderivative of f. So there's a couple points to be said about this. If you have a question, though, I know we really, lots of scary symbols and stuff, but this is the language of math. So if you have questions, let me know. All right, so before we get anything freaky and scary, let's just look at how easy this can be to use. So let's go to the next page and look at a couple basic examples. So the one integral we did a myriad of times was x squared dx. And so to compute this number, what we do is we say, okay, what function are we integrating? What is what we call the integrand? And the integrand is x cubed over 3. And so the way we would write this is we would write 1/3 x cubed, and then we use this vertical bar. And the vertical bar is a sort of a shorthand to say evaluate this expression. And so we plug in the first guy, which is 1 cubed, and then we plug in the second value, which is 0, and that gives us 0 cubed. And of course, this is nothing more than 1/3. So if you have a question or a comment, please ask. So let's change the problem now. Let's say we want to integrate cosine. We ask ourselves, what is the antiderivative of cosine? And the answer to that is the sine. And then we plug in. So you get sine of pi minus the sine of 0. Sine of pi is 0. Sine of 0 is 0. So this guy equals 0. And we'll do one more. Does anybody have a question? Actually, we'll do 2 more. So let's say we integrate from 0 to 1 of 1 divided by 1 plus x squared dx. The antiderivative of this function turns out to be the inverse tangent, or the arctan. And so if we plug in these values, you get the arctan of 1 minus the arctan of 0. The arctan of 1, for those of you who don't remember, is pi over 4. The arctan of 0 is 0. And so this integral is equal to pi divided by 4. All right, let's do one more of these, what we call, basic ones. Say I'm going to integrate 4 to 9 of of the following. The square root of x dx. So to integrate the square root of x, what you need to remember is that x in the 1/2 is the same thing. So when you add and do your antiderivative, x to the 1/2 plus 1, this guy becomes 2/3 x to the 3/2 from 4 to 9, which can be written as 2/3 times the quantity 9 to the 3/2 minus 4 to the 3/2. Now this looks quite frightening, but it doesn't have to be. 9 to the 3/2 is the same thing as 3 cubed, so this is 27, and this is 8. So you get 27 minus 8 is 19. And so this equals 38/3. So I'll let you think about that. If you have a question, let me know. About any of the arithmetic, maybe if I made a mistake. Any questions, comments? All right, so these are what we would call basically 4 elementary examples of integrals. The reason I'm calling them elementary is because if you understand your basic derivative rules, then that means you understand your basic antiderivative formulas. So these are not, there's no creative thought here. It's either you know them or you don't. Now, that doesn't mean every one of you has these memorized like this, but these ones do not require any creativity. They just require, do you know the derivatives or not? Do you know the antiderivatives or not? Any questions? All right, so it's also important to remember that they're not all that easy. So in general, integration requires much more creativity. Why? Because the antiderivative is not always obvious. So you're familiar with a little bit of this. We showed you one way to handle this in some scenarios. So in some scenarios, we can use what's called a substitution. What that really is you're changing your variable. So let's look at an example or two of this. Okay, so let's suppose we want to integrate the square root of 3x plus 1 dx. And let's say we want to go from 0 to 1. Now, we can't just go write a formula down like we did before unless we're really, really good, because we don't know the antiderivative of this function. So one strategy is to take what's inside the radical and replace it with one letter. So if I take 3x plus 1, I can replace it with the letter u. And so then the integral becomes the square root of u. Now, I can't just leave everything else the same because I'm changing from one variable to the next. I'm doing a substitution. I'm going from the world of x's to the world of u's. And so that means my bounds will change and my differential will change. So if I look at this formula down here, if u is equal to 3x plus 1, then we know du dx, the derivative, is equal to 3. Another way of writing this is that dx is 1/3 du. Now, if I replace my dx with that, I get a 1/3 out front. I can pull numbers outside of the integral, and this is du. And then I also have to consider the fact that my bounds could change. So when x is equal to 0, what is u? U is equal to 1. And when x is equal to 1, u is 3 plus 1, which is 4. So now my bounds change. My lower bound is now 1, and my upper bound is now 4. So what by replacing x with u, I took an integral I wasn't sure how to compute, and I've converted it to one that theoretically I should know. Because this is now 1/3. Now, what's the integral of u to the 1/2? Well, we just did it in the previous problem. This becomes 2/3 u to the 3/2, and we are evaluating from 1 to 4. So you can write this as 2/9 times 4 to the 3/2 minus 1 to the 3/2. Which becomes 8 minus 1, so 14/9 is the value of this integral. So if you have a question, please let me know. If you think I made a mistake, please let me know.
Professor, I have a question.
Yes.
So whenever we do the substitution U or whatever it is, we should find the new bounds?
Well, okay, so we talked about this last semester. There's two options. My advice is to do it the way that I just did it, where I found new bounds. But you can also leave things without bounds and then plug X back in after you integrate. But you got to be careful when you write it that way, because if I would have written that second integral, like if you see where my pen's floating around, if I would have left this 4 as a 1 and then this 1 as a 0, that would have been incorrect. It would have been writing nonsense, even if you get the answer right at the end. Here, the logic is sound. If you read this line of equations, there's no flaws in the logic. Whereas, you know, if you don't want to, so let me show you how you could write the problem. Maybe I'll just write it down to help explain what I'm saying. So alternatively, so if you didn't want to write it that way, suppose you didn't want to switch those bounds. If you wrote this, this is wrong. This doesn't make any sense. Do you understand what I'm saying? Now, what you could do, if you wanted to be very clear and clever, I guess, is a way of thinking about this, and I mentioned this last semester, you could write here x equals 1, x equals 0, so that the reader knows those bounds correspond to the original variable x, not u. Does that make sense? Maybe.
Yes, that makes sense. Thank you.
And then if you do it this way, you could write, what's this integral? Well, we know this. This becomes 2/3 u to the 3/2. And you can evaluate this from x equals 0 to x equals 1. But now, if you want, you can write this as 2/9, and instead of writing u, you can put your x back in. And then you no longer have to make sure the reader knows what's happening. So now you plug your values in, and you get 2/9, and then you plug in 1, so you get 4 to the 3/2 minus 1 to the 3/2. Then, of course, we know that this equals, right? It equals 7, so 14/9. So this is a correct way of writing it, and so is the previous page. But one common error that I'll see is that students will just write, they'll do it this way, but you won't get your bounds correct. And then at the end, you either replace them back correctly or you forget to put them in and you get the incorrect answer. So what I would encourage you to do is you study these two examples and try to make sure you understand why I'm making a big deal about it. Hopefully. Does anybody have a question? About these examples? Okay, so very good. Okay, so what else did we do at the end of last semester? Well, let's sort of remember that we also covered applications of the integral. So what were some applications? We understand area was one of them. We had this thing called average value, which is very important. We had this thing called motion along a line. So on the very first homework that we assigned to you, we'll give you some questions that ask you to do that, those kinds of things. And then what we're going to do starting Thursday is we're going to discuss new applications. So that's kind of where we're at. So we can think of the integral as purely just some abstract mathematical thing, which is perfectly fine. But we also understand that it can be interpreted in many ways, depending on the context. In certain contexts, we can interpret an integral as area of a two-dimensional region. In other contexts, we can interpret it as average value of a function. We can interpret it as the motion along a line. So, you know, for example, the integral can be used to answer questions about where an object is that's falling. We can use the integral to understand perhaps how, if I have a mass hanging on a spring and I pull it down from equilibrium as the spring oscillates, we can use integrals to determine where that mass will be at any given time. So there's lots of different applications of the integral, and we're going to learn about some more of them starting on Thursday. Now, these applications are all well and good, but if you don't know how to actually compute the integral, well, then we're in trouble. So you have to be, have to be able to compute it, and you have to be able to interpret it if the context requires that. Okay, does anybody have a question? Okay, so what I would do if I were you to get started is I would start reviewing my calculus. For instance, the last homework you guys had last semester would be a good place to start. You don't forget to check Canvas tonight or tomorrow morning at the latest, so you can see the syllabus and you can see our first set of homework problems that you can sort of start working on and ask questions Thursday. All right, does anybody have a question? All right, so here's what I'm going to do. I'm going to stop this. We're done for the day. I'm going to upload this stuff to the internet, and when it's all ready for you later today, you'll be able to check it out on Canvas. All right, so I'm going to stop recording now.